Now let's do some examples, specific examples of definite integrals with particular functions and the limit or the sums version. Okay, so we're going to look at examples of definite integrals and sums. So the first example, let's consider, assume for all of these examples that f of x equals the square root of x times the natural log of x, okay? So that's the function we'll look at here. And for part A, what we want to do is write an integral representing the area under that function, under f of x, on the closed interval from 1 to 2. Okay, so let's find an integral that represents the area under that curve from 1 to 2. And notice that this function is continuous and differentiable over this interval. So that makes this, we don't have any issues. We don't have any like jumps in the graph or anything like that. It's certainly continuous. All right, so we want the area from 1 to 2. So we're going to do an area from x equals 1 to x equals 2. So it's got to be with respect to x. And so I've got the area from x equals 1 to x equals 2. Remember, dx tells us that these are x values. And then the function we're going to integrate is the square root of x times the natural log of x. So that's all there is to it. This means the area under this curve from x equals 1 to x equals 2. Okay, so that's pretty simple. Part B, express this area as the limit of a Riemann sum. Okay? Express this area as the limit of a Riemann sum. And so we're definitely going to have the limit as the number of rectangles n goes to infinity of a Riemann sum from an index of I equals 1 to the nth rectangle of the area of each rectangle, which remember is f of x sub I, that's the height of the rectangle, times the width of the rectangle. And so in this particular case, we know our function is this guy. And by the way, you could put an asterisk on here if you like, either way. So the limit we're looking for in this particular example is the limit as n goes to infinity from the sum from I equals 1 to I equals n of f of x sub I is this function where x sub I is the input. So we'll have x sub I times the natural log of x sub I. Again, you can put an asterisk on those if you want. And we have the square root of all of that. So to calculate the height of each rectangle, for this particular function, you plug the x values into this to calculate your y. So that's the height of each rectangle, and then times delta x. Okay? And so what you start to see, and if you want, you could say on the closed interval from 1 to 2 to identify where your x sub i's live. You'd be dividing your interval from 1 to 2 up into n rectangles, and then you'd go from the first rectangle to the nth rectangle, calculating these areas and add them together. Now, I do want to point out the similarity between the integral and the limit of the Riemann sum. So in your integral, you have this dx. One way to think of dx, we'll sort of solidify this as we go further in this course. Dx is like an infinitely small version of delta x. So those two guys sort of have this relationship as such. Delta x it actually has a width, an established width. It's based on how many rectangles in you cut your area into. dx is when you have an infinite number of rectangles. dx is an infinitely thin version of this. The other thing is the height of individual rectangles can be calculated in this function like this, which corresponds to the integrand up here where you don't have the x sub I in the integral. You're just saying, well, it's just that function. That's how you calculate heights of all the rectangles, okay? So notice the similarities between the integral and the limit of the Riemann sums. Also, whenever you take this limit, this sigma turns into this elongated s. Now the tricky part is, in your integral you don't have an index at all. You just use the limits of integration, your x values from 1 to 2. So that's where the differences lie. But I wanted to point out the similarities and differences of your limit of Riemann sums and your definite integral. All right, so part C now, though we've got some of the notation figured out. For part C, let's do this. Approximate the definite integral from 1 to 2 of the square root of x times the natural log of x dx using right endpoints with n equals 4. Okay, using right endpoints with n equals 4. And what I mean here is use rectangles to approximate the value of this definite integral. And so what we're going to do is we need to find the area under this curve using rectangles from 1 to 2 and right endpoint. So what I'm going to do, rather than draw out the curve, I'm not worried about that. What I'll do instead is I'll just kind of think about the width of my 4 rectangles and the height of my 4 rectangles. And then I'll multiply those together and add to get my area. So this is 1, this is 2. And I need to divide this into 4 equal pieces. So this total distance is 1. So let's identify that here. Delta x, the width of each rectangle, is your right endpoint, your right x value minus your left x value. That gives you your total distance. Divided by your n, how many cuts, how many pieces you want to have, which is 4. So delta x is 1/4. So we're going to cut this into, we're going to increase our x values by 1/4 every cut. So there's the halfway point, there's the first quarter, there's the second quarter. So delta x is 1/4. That means that this x value is 1 plus 1/4, which is 5/4. Add another 1/4. Add another 1/4. And so now we can kind of see our x sub i's in this case. And we're talking about right endpoints. So the first right endpoint is going to be this guy, the second right endpoint, the third right endpoint, and the fourth right endpoint. So those guys are the 4 x sub i's that we'll use. So we can say now that the definite integral from 1 to 2 of the square root of x times the natural log of x with respect to x is approximately equal to the height of our first rectangle is determined by this x sub I. So I could say f of 5/4, right? That's the height of that rectangle times the width of my rectangle, which is 1/4, plus the height of my second rectangle, which is f of 6/4, times its width, which is also 1/4, plus the height of my third rectangle times its width, plus the height of my fourth rectangle times its width. And so now you can calculate this value on your calculator lots of different ways. You could, for example, you could store this function formula into your calculator and as f of x, and then you could literally type this out with f of times a fourth plus f of times a fourth, or you could manually do something like f of 5/4 is the square root of 5/4 times the natural log of 5/4, and multiply that by 1/4, and you could do that 3 more times and add all that together. In any case, at this point, it's a calculator exercise, and I did it using the function feature of my calculator, so I was able to type all of this in, and it looks like I got approximately 0.8688. So this definite integral, the area under this curve from 1 to 2 is approximately, and I don't have to write approximately every time, I already wrote it here, is approximately equal to 0.8688. And that's using right endpoints with 4 rectangles to get the approximation, okay? So you could use midpoints, left endpoints, more rectangles, fewer rectangles, etc. Since we're only using 4 rectangles, it's likely that this isn't a very good approximation for that area or definite integral. All right, let's finish up with a couple examples where now we'll look at a limit of Riemann sums and we'll have to figure out the corresponding definite integral. So let's write each limit as a definite integral, okay? So, number 1, well, let's look at the limit as n goes to infinity of the sum from I equals 1 to n of the expression x sub I squared plus the cosine of x sub I times delta x on the closed interval from 2 to 4. Okay, so this, again, it's an exact value in an exact area because we're taking the limit as n goes to infinity of the height of the rectangle times the width. That's the area of each individual rectangle, adding those together, and then taking the limit. All right, so this is, we want to write this as a definite integral. So it's going to be an integral from x value to x value. The x values we have here are from 2 to 4. And they're x values, so we're going to put dx for our independent variable. Now all that's left is the function that we're integrating, and that, remember, delta x corresponds to dx, and this corresponds to your function. The only difference is here you don't need the I subscript. So our function is literally just the function x squared plus the cosine of x. Make sure you put parentheses around this because you've got the sum here. So you want to integrate all of this with respect to x, and that's all there is to that. This integral represents the same area as this limit of the Riemann sum. Example 2, let's do it again one more time just to see. Let's look at the limit as n goes to infinity of the sum from I equals 1 to n of the fraction e raised to the power of x sub I star plus 1 over e raised to the power of x sub I star minus 2 times delta x on the closed interval from 1 to 6. Okay, so I want to do an example where I use the star in my x sub I and one where I didn't, because either way is fine. Remember, the star just indicates that it could be any x value in each of the intervals for your rectangles, no big deal. But in this case, we're looking at a definite integral from 1 to 6, from x equals 1 to x equals 6, of the function e to the x plus 1 over e to the x minus 2. And because this is a fraction, not a sum or difference, I don't need parentheses, and that is the definite integral for this limit of Riemann sum.